Welcome friends.
Welcome.
Hope you have followed the part 1 of metallic bonding. If you have missed it, just click on the reference window or in the I button on the video, or you can go to the description section below to get the link.
How can I clear my queries?
Put your queries at the comment section at the end of this page. You can also express how useful was the part 1 for you.
How can I follow this channel?
If you find it useful, then push the subscribe button to get more interactive videos on different topics of chemistry in future for free. What is the color of your subscribe button? Red. Then touch it and make it gray.
Yeah. I will surely do.
Well, let's go to the part 2 of metallic bonding.
Valence bond theory. We are all aware of valence bond theory. Here we will apply the theory in case of metallic bonding. First, we will discuss about the short period elements means from lithium to neon and sodium to argon. Yellow shaded elements. Then we will move to long period element, which are under blue shade here. We are selecting lithium as a representative member from short period elements. Lithium is a very useful metal with electronic configuration 1s22s1. Classical covalent bonding involving two electrons between two centers are well known. That is 2C2E bond. A particular lithium atom can involve in covalent bonding with two other lithium atoms alternatively. So, in two dimensions, we can observe continuous bond swapping producing canonical forms. Now, if we consider, some lithium atoms lose one electron each to become lithium cations and some become lithium anions by accepting one electron each. Lithium anions now can create two covalent bonds with two lithium atoms. The lithium cations will remain sole because they are unable to form any covalent bond. Alteration of charge in between cations and anions will result in demolition of the said bonds and will similarly create two other bonds. Involving such alterations in between the canonical forms, and extensive resonance will operate, which leads to high cohesive forces between the atoms. This is the reason why metals forms hard lattices. Now, question is, how lithium anion involves in two covalent bonding. Electronic configuration of lithium anion is 1s22s2. So, there are 1s and 2s orbitals, which are doubly occupied. But, in metallic lattice, the electron distribution rearranged as 1s22s1 2p1. 2p orbital is involved, and thus, 2s and one of the 2p orbitals get singly occupied, which are responsible for two covalent bonds. Two of the 2p orbitals remain vacant, which are responsible for electrical conduction when external field is applied. These vacant orbitals are called metallic orbitals. Okay. What will be case of long period metals? Let us consider tin as our choice. It's a group 14 element. Unlike short period metals, these metals have N-1d electrons. So, the situation is going to be a little bit complicated. All the valence electrons may not participate in bonding purpose. Many factors like inert pair effect may resist the valence electron to be involved in bonding, especially for the heavier elements. Have a look at the table. Tin has two forms, Sn, A, and Sn, B. Tin at state A has electronic configuration 4d105s15p3 and at state B has electronic configuration 4d105s25p2. There are completely filled d orbitals and singly filled s and p orbitals in case of Sn, A, and thus it has 1s and 3p orbitals to be involved in covalent bonding. There is no vacant orbital, or we can say no metallic orbital. So, Sn, A, behaves as insulator. Below 18 degrees Celsius this state is quite stable. This is called gray tin. In contrary, state B of tin has only two singly filled p orbitals which can form covalent bonds. One p orbital is vacant, called metallic orbital. Rest of the orbitals are completely occupied. As this form possesses one metallic orbital, it can show metallic character. Here we can observe inert pair effect. Similar situation can be observed in case of zinc. There are three forms of zinc: zinc A, zinc B, and zinc C. Only state A has no metallic orbital, so it is non-metallic. Though the three forms of zinc are not reported separately, it is believed that all the forms contribute to the zinc structure in different ratios depending upon the situations, like temperature, pressure, etc. There are some situations where all the unpaired electrons in D shell may not participate in covalent bonding. Some of them remain non-bonded. Such orbitals containing those electrons are called nonbonding orbitals. These orbitals remain non-bonding because of the steric hindrance. Considering such situation, we can explain the paramagnetism of the metals. Nickel is one of such examples. It possesses two state A and B. You can easily find that nickel A is paramagnetic but non-metallic covalent structure, while nickel B yields the diamagnetic but metallic structure. In practical life, we have nickel as a mixture of both in different proportions, and thus resultant paramagnetism is observed. Merits and demerits of valence bond theory. Merits. Using valence bond theory, we can explain different properties of metals, like: Number 1. Trends of cohesive energy. Number 2. Electrical conductivity. Number 3. Distribution of metallic properties in periodic table. Number 4. Paramagnetism in metals. Number 5. Explanation of allotropic forms. Demerits. Compared to the molecular orbital theory, the valence bond theory appears more empirical. In case of VB theory, we mostly depend on observation rather than theory.
Hi. I'm Johanna the robot. What are you doing today? I'm working hard with Manos to help you during the lockdown going on. Threats of coronavirus will be ended one day. Normal life will be restored. What's about your study? Is it going in full throttle? If not, you may suffer in near future. Work hard. Utilize the time.